First monosaccharide, glucose. Glucose is probably the best known monosaccharide. Technically, it's a aldohexose, mean it having a aldehyde as a functional group in the polyhydroxy molecule, and having a hexose, mean 6 carbon atom. It's also known as the dextrose. Here, D-glucose, as we already discussed, we are looking at that last asymmetric carbon center, last chiral carbon center, and according to it, it is on D left right side, so it's a dextro. We are giving a D notion for it, so it's a D-glucose. Further, this is a linear structure that we have discussed, but in real world, linear structure is not justified. Why? Because certain chemical test has been done on the glucose molecules, and we already discussed about it. So despite having an aldehyde group in linear structure, when we do a 2,4-dinitrophenylamine phenylhydrazine test, then it doesn't give any of this test. 2,4-dinitrophenylhydrazine test is not positive. Hydrogen sulfide test is not positive, because if aldehyde is there, a pre-functional aldehyde group do exist for a glucose, it must give all these tests, because these are tests for a aldehyde functional group. So this confirms first point, aldehyde is not available as a free functional group, because if it would have been there, then 2,4-dinitrophenylhydrazine would be positive, because in free functional group, if this free aldehyde group do exist as we show in linear structure, this hydrazine would have combined with the carbonyl oxygen to give us this complex, but it doesn't form hydrazone. So first possibility of free functional aldehyde group is discarded. It's not possible. Next, when we treat glucose with acetic anhydride, what we'll see, consumption of acetic anhydride is for 1 glucose molecule to 5 acetic anhydride molecules. What it means? There are 5 hydroxy functional group do exist in glucose molecule. That's what we saw. 4 plus 5, and they combine to give us this ester of glucose. 5 ester bonds are formed, but still, it is possible. So now we know from that aldehyde test, this aldehyde is not available in a free functional position. Second, 5 hydroxy groups are there now. So that is confirmed. 5 hydroxy groups do exist in glucose. So what should be the actual structure of glucose then? Further, again, this pentastate structure is we have reacted it again with hydroxylamine, which is a reaction of aldehyde to make oxime, but it's not possible. Again, the test is negative. There is no reaction. So it confirmed that somehow we having only the possibility of a cyclic structure where aldehyde is not available readily for reaction. That's what we are expecting it to happen. This is the fifth hydroxyl group. It reacts with this aldehyde in the first position to make a ring. So what studies has confirmed? Hydroxyl group at C5 carbon atom adds to the aldehyde to make a cyclic hemiacetal structure, which is a six-membered ring. So remember, in real conditions, glucose molecule do exist as a cyclic hemiacetal structure. Hemiacetal means because of only one acetal group here, and it is a six-membered ring resembling to pyrrole. And now, because what we see here, because of this hydroxyl group's addition to the aldehydic position set C1, there are two possibilities. One is a hydroxyl group is on left side. One is hydroxyl group will go to right side in the structure, up or down. If we look at a planar form of this, either it can go in one direction or the other direction. So we have here two forms known as the alpha forms and beta form, which are known as anomers. This six-membered ring, because it resembles to pyrrole, so it's called as a pyranose structure also, like dextrose. We already discussed the possibility of two cyclic hemiacetal. That's what we see. If OH group is on one side, that is on the right side, here it's already, then it's a alpha glucose, because if you make it up after the reaction, this is C1 position, this is C2, this is C3, C4, C5 and C6. And C5, because of C5 is on a right side, so in glucose, so you say D-glucose. And here, OH is looking at the downside. Other way, or on the same side, here it's upside. If we hydrolyze it, it will go to the left side. It's called a beta D-glucose. So how we will call a glucose as alpha glucose or beta glucose? These two anomeric hydroxyl groups positions decides it. If this hydroxyl group is on the same side as our D-glucose, meaning cis to it, it's called alpha glucose. Here it is on left side, while our fifth last position of the hydroxyl group on carbon is on right side, so it is beta glucose. So on the basis of this anomeric carbon only, we call it anomer. And if this position is cis to this carbon center hydroxyl group, is called alpha. If it is trans to it or opposite to it, it's called beta. Ring closure creates chiral center here again, and that chiral center after the cyclic structure is called anomeric carbon. So what are the sources of glucose we have in our life? The most abundant source is sugarcane juice, which is also known as sucrose. If we concentrate this sugarcane juice by boiling and add H2SO4 to it, what we'll get? We'll get some breaking of that sucrose into glucose and fructose, that is in equal quantities because they are in equimolar positions. That's what is sucrose is. One glucose molecule and one fructose molecule, they go into hydrolysis to give us a glucose and fructose. That's what we'll get. So sucrose is a combination of glucose and fructose. And whatever glucose we buy from a market under any commercial name, it is obtained by the hydrolysis of starch or corn flour. What is a starch? Starch is a polymeric chains of glucose. When we boil it with H2SO4, we'll get individual glucose units. That's what our starch is. It's a polymeric chain of a alpha D glucose. The hydrolysis is to get a individual glucose molecules. Next is fructose is a molecular isomer of glucose. Formula is same but having a ketonic functional group at carbon second position compared to aldehyde in glucose at first position. Obviously aldehyde is always on terminal position. So for fructose, we having a 5-membered ring of fructose resembles to furan, so they are known as furnose, like pyranose for glucose, which is a 6-member carbon ring. But here furnose, because it is a 5-membered ring, structure resembles to furan. Again, same assignment is done. First, lowest asymmetric carbon will get the compound name. Here you see, we call it a alpha D, fructose. So in that, here is C5, the hydroxyl group attacks the second carbon, and that is a, what is that? That is our ketone. And that double bond opens up to give us a hydroxyl position. And again, this center is anomeric, just like in glucose, because hydroxyl group can go up or go down. Here it's a alpha, because hydroxyl group on the same side as here on C5 carbon center. When it is opposite to it, here hydroxyl group will be on one side and its transposition to it. Because a D dextro means it's on right side. Here this position will be on, if you opens it up, it goes to left side. So it's a beta D fructose. Here we will discuss our Howard structures. These structures are known as the Howard structures. How we get it to different anomers. You see here, if we opens up a ring here, let's say this is the open ring structure. You see, this CH2OH, this is the one, C1. C2 is a here, double bonded. In open structure, it's a mix a carbonyl group. And C3, this is goes to a left side, C4 on again right side, C5, this one on a right side. This is a D-fructose. But what happens when this opens up in anomeric form? You see here, this is the anomeric hydroxyl group only. And where it is? The CH2, C1, C2 and C3. This one is C2 hydroxyl. If it is on a same side, that is on a cis side to it, there is cis, this group will come up here, hydroxyl group. It is cis position, so it's a alpha D glucose. So alpha D fructose, that's the alpha D. But the next structure, next anomeric structure, if you look, hydroxyl group can go up when this, this hydroxyl C5 position attacks here, and we get a pyranose structure. So here we getting a for furnose structure because it resembles to furan. Then what happens? It is on left side while this is on right side. this OH will go here, because after it opens up, you see, if you look at it on hydrolysis, this will come up here and this will go up on top. So it is beta D glucose. Remember simple point, if this anomeric carbon hydroxyl group is on the same side or on a right side, in this case, if it is on a right side, then it's the alpha. If it goes to left side, it's beta. That is the case for a D glucose. The D means dextro, and dextro is decided by the last chiral carbon center, which is having a right. So cis case, it is alpha.